Okay, so I want to today go into gradient flows in the Wasserstein metric, and we're going to see actually there's some really deep connections between the Wasserstein metric and optimal transportation and a number of other PDEs, some of which you're very familiar with, some of which much less is known about, and this would actually give new insights into how to analyze these PDEs, how to do numerics for these PDEs. So I'm not going to go into every technical rigorous detail on this topic, but I want to give you an overview at least of what's going on here. And this is come about in a paper by Jordan, Kinderler, and Otto. In 98, and these are actually often known as JKL flows. Okay, so we're going to think about the idea of trying to minimize some functional, and obviously there's different ways that you could minimize functionals, but one way would be via a gradient flow. You take a gradient of the function and you move in the negative gradient direction to try to decrease your energy. Okay, so let us suppose that f is some function. I'm going to start very simple, and then we'll try to generalize. So for now, let's suppose this is convex. We won't really need this to be convex later, and we want to try to minimize this. And so we want to minimize capital F of x. Okay, and we're going to do this via a gradient flow. We find the direction F decreases fastest, and we move in that direction. Okay, that's nothing shocking, hopefully. If we move in the negative gradient direction to a gradient flow, that will look like this. Okay, so we're solving this system of ODEs where the change in x is determined again by the negative gradient direction. Okay, and we start somewhere. Okay, and now we want to discretize this. So how would we say discretize this in time? What are some good options?
Euler?
Euler, sure. Forward Euler, backward Euler, those are the simplest options probably. So let's think a little bit more about backward Euler. And what I actually want to do is bring this into a framework where at the discrete level we have a scheme where we don't actually need to be able to take gradients of f. And somehow we'll have a concept of a gradient flow that doesn't necessarily actually require us to even need gradients. A weak sort of formulation, if you like. So say we do backward Euler. Discretize in time. Okay, so what happens? We have, I'll let tau be our time step here. And then I'm going to have the gradient of f evaluated at our new time. And we do this for some small value of time. Okay, so let's try to rearrange this a little bit. Again, my goal is to sort of put this in a form where the gradient of f doesn't strictly appear. Okay, so I'm going to just bring this all over to one side. And I could write this as a gradient of something is equal to 0, right, with the appropriate something. I just need a quadratic term. So if I want to do that, let's write this as the gradient of We'll evaluate this at xn plus 1, obviously, because we have an sn plus 1 here. Let's make this as x minus xn squared over 2 tau plus gradient of f, plus f of x. Okay, evaluated at x equals xn plus 1, and this is equal to 0. So from here, do you have any ideas? How could I alternatively write a scheme for updating xn plus 1 that didn't actually require gradients? Do you have any ideas there? So I'll rephrase the question a little bit. I'm setting the gradient of something equal to 0. What does setting the gradient of something equal to 0 tend to do or help us find?
Local minimums?
Minimum, sure, right? In this case, this should have a minimum, right? This we said is convex. It's not actually necessary for this to be convex to have a minimum, but it's certainly sufficient. This is convex. So the gradient of this equal to 0 is equivalent to finding a minimum of this function here. Actually a global minimum because what's sitting there is convex right now. So this could be equivalent to saying that xn plus 1 is a minimizer of all of this. And this could kind of give us another way of viewing a gradient flow, right? A weak formulation of a gradient flow, if you like, where I don't really need this to be, I started by saying this is convex and presumably differentiable. But to do this scheme, I don't really need this to be differentiable, certainly. All I need is that this has a minimizer. Okay, this is nice, obviously. This really I just need to be lower semi-continuous, and I've got minimizers. So this scheme needs some regularity. It needs us to be able to make sense of gradients. This scheme doesn't need much in order for it to make sense. And this scheme generalizes. So I started really simple. I said I have a function on Rn. But I could imagine maybe I don't want to work on Rn, maybe I want to work on some much more general metric space. So doing this on a more general metric space, we'll have to think hard about how to make sense of the gradients. But doing this on a general metric space, you can write down in one line what this kind of scheme will look like. So let's imagine now that we want to do this on a more general metric space. So we can define this kind of scheme. On the metric space. Okay, let's say capital X is my space and D is the metric. Okay, I want this scheme to make sense. So let's see what needs to be true about f. F is going to be a function of the metric space, real valued. I want to be able to find minimizers, so I need this to be lower semi-continuous and bounded below. Okay, now right away I can write down the same scheme, almost the same scheme. The difference here is that I'm not going to just put in x minus xn squared, right? What am I doing here? I'm looking at the distance between x and xn, right? So now that distance is going to come from the appropriate metric on this space. Okay, so let's look at this. Let's define xn plus 1. I'm going to use my time step as a subscript. Obviously, exactly what I compute is going to depend on the time step. And now I'm going to use the same scheme, the argument of f of x plus Okay, the distance between x and xn squared, so that's my metric. Divided by 2 tau. And now what you'd like is to be able to make a connection between this scheme and some sort of continuous flow like this, right? This is a time discrete process. We want to relate it to some sort of equation like this, some sort of PDE, hopefully. Okay, so what are we going to do? We need to think about limits as tau goes to 0. Okay, so first I'm going to interpolate. Interpolate the time discrete approximation onto all time. Lots of ways of doing this. So one example would be just to do something piecewise continuous. So I just define a function of t to be just a piecewise constant extension of this thing. Say if t is between n minus 1 tau and n tau. There's other extensions, obviously, you could do. And then we say, okay, so for each small time step, this gives us some sort of function of time. And now what happens in the limit is we take this time step to 0. Do we recover some sort of equation like this? And what kind of equation is it? What kind of flow are we getting? So let's study the limit as tau goes to 0. Okay, again, I'm not gonna do all these details rigorously. I'm gonna give you an overview, but I want to at least show you where we can get some kind of PDE out of it, and again, a wide range of PDEs depending on the particular choice of f that you use here. Okay, so I said we're talking about gradient flows in the Wasserstein metric, so we're going to be particularly interested in X being a space of probability measures, and D being the Wasserstein 2 metric, say. And this ends up giving us some really interesting results just in this special case. So let's do these functions.
I have a good question.
Yeah.
Does this only work with the Wasserstein 2 metric?
You can do this with other metrics too.
But will you have that form then? It seems like the analogy with taking the gradient somehow.
Yeah, so the gradient, this isn't going to be, this is a gradient is defined with respect to a particular metric. So the gradient is defined with respect to whatever metric, whatever D is, D go.
Right.
So we could put, you can put whatever metric space you want here. Now, your ability to analyze this and say prove things about limits as tau goes to 0 is going to depend on the particular metric space that you use, certainly. You can do other Wasserstein spaces a lot. Wasserstein 2 has been studied the most. General quadratic cost optimal transport has been studied the most. And there's some good reasons for that, and one is that it actually comes up a lot in applications. It's particularly interesting, but you can certainly, you can put the Wasserstein P here, certainly. Okay, so let's do this. Let's consider f being a function on the space of probability measures on a domain omega. Okay, and t being W2. And what assumptions do I want? I'm going to assume that omega is compact. That's a pretty standard assumption that we've made all semester. You can prove things in some cases with non-compact omega. It's harder. So let's assume omega is compact. And as before, f is lower semi-continuous, and it's bounded below. Otherwise, these these JKO type schemes don't make sense. Okay, so certainly the scheme is well defined. Now we want to relate it to some kind of flow. Right here, we started with this idea of a gradient flow. We've done flows before involving optimal transport. Last week we did flows involving optimal transport. Right, we had this Benjamin-Grenier formulation where we said we're going to flow one density into another density. Right, and we had this sort of fluid flow framework that gave us an alternate definition of this Wasserstein metric. So we're going to start with that as our idea. We're trying to come up with a PDE. We've seen PDEs that flow probability densities before. The continuity equation was our starting point. Right? So we previously used the continuity equation. And that was rho sub t plus the divergence of rho v equals 0 to flow densities. So what's our goal here? Our goal is to find a velocity field v. That was our goal last class, to find the right, we know we can flow probability densities this way. Now we want to find a velocity field v such that this flow that we get of a probability density agrees with this flow in the limit as tau goes to 0. Right? In the limit, if this limit as tau goes to 0 exists, we get some sort of flow of a probability density. This is a very kind of general way of flowing probability densities, and you can put all sorts of different velocity fields here that we want. We want the right velocity field such that this flow agrees with this flow. So this is really our goal. Let's find the velocity field v such that this flow is equivalent to whatever we would get. So the solution of this flow would agree with the limit as tau goes to 0 of our x tau. Okay, so I expect that my gradient flow equation, this is my gradient flow equation in the simplest case. I expect that in general, on probability metrics, when we're doing gradient flows in the Wasserstein metric, my gradient flow will look like this. I just don't know what v is yet. And then v is, of course, going to depend on whatever f is that we started with. Okay, so we need to think more about this. So in order to figure out what happens with this scheme, we really need to think more about the optimality condition for this. So we know, we've set things up, this is certainly a well-defined scheme. Let's think a little bit more about what sort of equations the minimizers would satisfy. So how would you go about finding a minimizer? Take the gradient, or more generally, take the first variation of this thing. Yeah. So let's investigate the optimality condition by doing exactly that. Okay, let's investigate optimality condition in the JKO scheme. So we need to compute the first variation. So I'm going to do a quick reminder of what is the first variation, in particular what this looks like when we're working with probability measures. Okay, so we need to compute the first variation and set it equal to 0. Okay, so analytically, this is where we have to be careful. This issue came up on a homework assignment early in the semester. So when we're computing the first variation, right, we're perturbing things, so we have to be careful how we're perturbing things, right? Because I can't just put anything I want in here and have f make sense. F only makes sense if I plug in probability densities, right? So if I take a given probability density and I perturb it, the result of perturbing it has to still be a probability density, or it will simply not make sense to plug it in here. So that's the one point where we have to be really careful. Okay, so say we want to perturb rho. Rho, again, is a probability to rho plus some epsilon chi. And again, we need rho plus epsilon chi to also be a probability. Otherwise, f doesn't make sense. Okay, so that's, it's not a complicated point, but it turns out to be an important point. And you'll get the wrong result if you don't keep this in mind. So let's restrict ourselves to chi such that, call this sigma. This is a probability, okay, for all sort of small epsilon greater than 0. Okay, so in other words, what do I want? We're going to write rho plus epsilon chi as, okay, what is epsilon chi? Epsilon chi is sigma minus rho. Let's see, how do I want to write this? Maybe I'll say it like this. We want, so look at perturbations of the form. Sigma minus rho. So I'll add this. In particular, let's say that sigma equals rho plus chi is also a probability. So what do we have? We have rho times 1 minus epsilon plus epsilon sigma. Okay, and as long as both rho and sigma are probabilities, this will be a probability, right? This looks like some kind of average of rho and sigma. So these are the kind of perturbations that will be allowed to take. So this is going to be a probability as long as rho and sigma are probabilities. Right? For small epsilon, epsilon between 0 and 1, this is always some kind of average. Okay, so these are the kind of perturbations that we want to take. Perturbations that really actually have this form. So we perturb by a probability, but we can't just add epsilon times that probability because that's going to potentially destroy the fact that we're a probability. It will destroy the fact that we're a probability. We have to average in this kind of way. We want perturbations of this form. So we're going to do this for all, say, sigma belonging to probability measures, and we'll do things that are bounded. Okay, then we can define the first variation. When we know how we're allowed to perturb, we can define the first variation. So this will give us a whole space of different probabilities. And now the first variation of f is defined this way. Okay, I'm going to call this Gf at T rho, evaluated at rho, is such that, well, what do we want? We want to perturb so rho plus, so it has to be a perturbation of this form, right? So we can write it as epsilon chi, where we understand that chi has this form. It's not just any old function that we're perturbing with. Right? We take the derivative with respect to epsilon. We set it equal to 0. And this should recover for us our first variation. Right? So we'll get integral of f d rho times chi and this should be true, again, for all chi of the appropriate form, of the form sigma minus rho. Okay, where sigma lives in this appropriate space. So probability density, and typically we take it to be something that's bounded and compactly supported. Okay, now, so there's one important thing to notice here when it comes down to the fact that we're only allowed to take perturbations like this, perturbations that are a difference of two probability densities. So what I'd like to do is say that this uniquely defines my first variation. It actually doesn't uniquely define my first variation. It uniquely defines it only up to additive constants. So let me explain. Okay, so we do this calculation, we get something over here. Now I'm going to try to add a constant to that something. Okay, well, in the first term, I get what I expect to see in my first variation. And in the second term, I can pull the constant out of the integral. And what is the integral of chi equal to?
0.
It's equal to 0, exactly. Because it's the difference of two probability densities, right? So chi was equal to sigma minus rho. If I integrate sigma, I get 1. If I integrate rho, I get 1. That means the integral of chi is indeed 0. And that means when I'm trying to use this definition of first variation, well, I could put this object here, or I could put this object plus any constant here, and they'd all agree with this definition of first variation. So in other words, the first variation in this case is defined only up to, defined, I guess, uniquely, only up to additive constants. So what does that mean? When we're trying to find a minimizer, what do we want to do? We want to take the first variation and try to set it equal to 0. What I'm actually going to effectively do is I'm going to compute something like this and say the best I can do is set it equal not to 0, but know that it's equal to a constant. Okay, so that's, I mean, it's a simple point in some ways, a little bit subtle, but it's actually important. We're not going to come up with the right kind of flows if we don't use the right kind of perturbations here. And we had some practical examples of that in the first homework assignment where improper perturbations led to wrong solutions. Okay, so let's now try to take the first variation of the object that we actually care about, the object that we're actually trying to minimize. So let's come back to this thing. Call it G of rho, which was f of rho, plus this term that involved the Wasserstein metric. So we had W2 squared, rho n, over 2 tau. And we need to compute the first variation of this, which, okay, this term, that's obviously going to depend on your f, right? So I can't tell you more about this term until you tell me what particular f you're trying to minimize. But we certainly also need to be able to compute the first variation of this Wasserstein metric. So we'll say this is 1 over 2 tau, the first variation of W2 squared, okay, and as I've written it here, we have 2 arguments here. We're only taking, we're taking the first variation with respect to this first argument. So it will be important to keep those straight, which is which. So the Wasserstein metric itself has symmetry. We're breaking symmetry a bit here. Okay, so again, this guy will do case by case depending on f. This guy we should be able to do once and for all. All right, so there's many different formulations of Wasserstein metric, optimal transport. It comes back to this optimal transport problem. So we can write it in that Kantor-Ovich formulation, and we get this minimization. We can write it in the dual formulation, and we get this maximization. As in probably many things, the dual formulation makes it a little easier to compute the first variation. The dual formulation made it easier for us to do lots of different things. So hopefully that's not a huge surprise. So let's try to write this in terms of the dual formulation. Okay, so what do we have? We have W2 squared, which is the difference between two densities. So remember, I'm going to be computing the first variation with respect to the first argument only. So this, I can write in different ways. So I can write it in terms of the Cantor-Ovich problem, which is an infimo. I'm going to just actually use half the quadratic cost instead of the quadratic cost. It's not that important. It's just, as in many things, x squared over 2, once you start taking derivatives and whatever, it just works out cleaner. So I'm going to put a 2 out here and let this be my cost. Again, it's not super important that you do that. It amounts to not having extra factors of 2 floating around later on. And this, we said in the dual formulation, is 2 times the maximum over all u and v of the integral of u times f plus the integral of v times g, subject to u of x plus v of y being less than the cost. And you can maybe see, just writing it in these 2 different ways, why I might choose to compute first gradation using the dual formulation. All right, I've got to, what do I have to do? I have to put an f plus epsilon chi everywhere it appears. Okay, I'm pretty happy putting an f plus epsilon chi inside an integral like this. We've got to work out what to do with the constraint. But I'm pretty happy putting a perturbation inside this integral. I'm perhaps less happy putting it inside this complicated looking constraint. So it's hopefully not a mystery that this is the formulation we want to work with. And I can drop the constraint because we know there's the relationship between u and v, right? We know they're going to be duals of each other. Say c duals with respect to this cost function. So I could alternatively write this as 2 times the maximum over all u of the integral of u times f plus the integral of u complement, or not complement, UC transform times G. And now, okay, this is an unconstrained problem, which is great. And the only place, right, f is looking at here, but the only place f appears now is right here. It doesn't actually appear at all in the second integral. The second integral is just looking at G, and we're not trying to perturb G. Okay, so let's write this down. We're in really good shape to be able to easily take this derivative here. So the derivative of f plus epsilon chi, okay, where we're going to set epsilon equal to 0, is equal to 2 times the derivative of this maximum at u f plus epsilon chi plus u transform and we're going to do this at the point where epsilon is equal to 0. So we've done things like this before multiple times, where we're taking the derivative of a maximum of things, right? And what do we have to do? We have to figure out which value of u achieves the maximum, and take the derivative and evaluate it at that value of u. Okay, so what value of u achieves the maximum? Well, since we're getting to epsilon equal to 0, right, this is just coming back to whatever value of u gives us our Wasserstein 2 here. Right? This is just our kind of typical u, our typical potential that comes up when we solve this dual problem. It's the u that shows up that we take the gradient of to get our optimal mapping. Okay, so if we're trying to take the derivative of this with respect to epsilon, what's going to happen? We're going to get a2 u chi here. Call that u star, where u star is the value that achieves the maximum in the previous line. U star is the value that achieves the maximum here. It's the typical u star that we find when we're doing optimal transfer. Okay, so here again, u star achieves the maximum in the previous line. Okay, so in other words, u star is simply the usual potential associated with half of the quadratic cost. Yeah.
Should that be the derivative of u star?
Should be the derivative of u star. No, so we're taking the derivative with respect to epsilon.
Oh, okay.
Right?
Yeah.
Is that okay?
Yeah.
The derivative of u star is important. In other words, the gradient of u star is important. The gradient of u star is what shows up in our optimal map when we're doing optimal transport. So when we do OT, the optimal map with this cost is, so remember, in this form, I didn't do this in terms of Lagrange transforms, which we know we can do with quadratic cost. I did it in terms of the C transform. So that means this map has the form of x minus the gradient of this cost inverse evaluated at grad u. What's the gradient of this cost? It's just an identity. Right, that's where it was coming in to stick the half in here. So the gradient of this is the identity inverse is still the identity, and then we'll plug in the gradient of this u. Right, in other words, this is of grad u, where we have h equals half of this quadratic term. Right, that's what we got when we did sort of general cost optimal transport. Okay, so we've got the first variation of W2 squared here, and it's nothing but 2u star. Right, I have that line still here. Yeah, so the integral of the first variation times chi. So here we've got the integral of 2u star times chi, up to additive constants. Okay, so this we can say, this term that we needed, rho, and rho n is 2u star. U star, again, being the optimal transport potential associated with the quadratic cost. Okay, and this is the optimal map from row to row n. So T of x equals x minus grad u is the map from row to row n. Okay, so if we go back to our JKO scheme, right, our JKO scheme was this. That we're trying to let rho at time n plus 1 be the minimizer of f of rho plus W2 squared rho and rho n over 2 tau. Okay, or written this more briefly as G of rho. Well, doing this sort of minimization, things all sort of well defined, everything's nice enough, should be the same as saying, well, the first variation of all of this, evaluated at rho n plus 1, which is only defined at the additive constants, is equal to 0. Okay, this we know the first variation of. This, again, is going to be very problem dependent. We'll do some examples. But this tells us that, okay, the first variation of f evaluated at rho n plus 1 plus the first variation of this guy. Well, the first variation of this guy. Here we had a 2u, and now divided by 2 tau. So this is u over tau, should be equal to a constant. At the minimizer. Okay, so I want to get rid of that constant, the kind of unknown constant on this side. So the easiest way to do that is to just take a gradient of both sides, right? And the constant goes away. I'm taking a gradient sort of makes sense because I actually kind of want to take a gradient of u here, because the gradient of u is what's actually important when we're doing optimal transport. So for a variety of reasons, it makes a lot of sense to want to take a gradient of this equation. So we'll say that this is the same as 0, the gradient of my constant is 0, is equal to the gradient of my first variation of f plus gradient of u divided by tau. And if we're doing optimal transport, which we are, we're working with this Wasserstein metric, so we are doing optimal transport. The gradient of u also has this interpretation as the optimal map, or the difference between where we started and where we're going. So I could write this also as the gradient of my first variation plus x minus t of x over tau. rewrite this a little bit, x minus t of x over tau equals the gradient of my first variation. Okay, this, again, once I know what f you are interested in, we can compute this. That's no big deal. This object, let's think about this. I think I have a sign f. I moved this to the other side. That's better. So let me ask you this. What are the units of this object over here on the left-hand side? What does it look like? It looks like a velocity, right? So this over here, this is a displacement, right? This is where we started. This is where we're ending up under the optimal transport map. Tau was our small time step that we were using to take us there. So this in fact feels like a velocity. We're looking for a velocity, right? What was our goal? We wrote down a continuity equation and said this should be the equation that describes our gradient flow. We just don't know the velocity. All of a sudden, we have a velocity popping out here. Okay, but what is this velocity of? This is velocity of a flow from, we said from rho n plus 1. Right? The rho n plus 1 is going to end up here. From rho n plus 1 to rho n. Now, of course, our flow is going the opposite direction. Our flow should be taking us from rho n and evolving towards rho n plus 1. But this is exactly the negative of the velocity we're looking for. We just have to put it in reverse. So this is backwards, but aside from being backwards, the flow we want should have velocity of the negative of this. So v equals minus this. Of course, that, okay, a priori, you have to do optimal transport to compute that, and doing optimal transport is maybe not easy. But we happen to know this object is also equal to the gradient of our first variation of f. And once we know f, we can compute that. So this is nothing but the gradient, negative of the gradient of the first variation of f. Right, so we had a time discrete scheme. In our time discrete scheme, this is exactly the velocity. If we're discretizing everything in time, this is exactly the velocity we'll see. Displacement in space over displacement in time. Negative of that. Now this becomes the velocity field associated with really our time discrete scheme. So this is certainly the kind of velocity we expect. In our discrete scheme. So now if everything works out, if we can take limits as tau goes to 0 and get the expected results, we're going to expect to get a continuity equation with this now as our velocity field. Okay, so I'm going to say if everything works out, as tau goes to 0, we expect our JKO scheme, to limit to this flow. Okay, so what was rho t minus the divergence of rho b was equal to 0. And now we have a candidate for V. This is a candidate for V. So what are we going to have? Rho t, this time it's a minus the divergence of rho, the first variation of f, equals 0. Okay, and this is the PDE associated with doing gradient flows of F. In the Wasserstein metric. It's called the W2 metric. Right, so we worked backwards. In our first example on Rn, I started by saying this is the PDE for gradient flow, and then we derived a time discrete scheme and worked our way to a time discrete scheme that didn't involve really taking gradients. Then we worked backwards. We introduced a metric space, and we said we like the same time discrete scheme. Like that makes sense. We can do it. It's easy. Now, how do we back out a PDE flow? And with a little bit of work, this is the PDE that describes that gradient flow. Any questions there so far? I'll do some examples.
Sorry, I'm a little confused. So is the overall goal to have F flow into rho? Is in the long time?
So the overall, so F is a function of rho, right? It's a function of probability densities. So the overall goal is to find minimizers of F by flowing in the negative gradient direction. But again, F isn't a function of Rn, so you need to define a gradient with respect to the appropriate metric. So the overall goal of this is to minimize F by flowing it in the gradient, by doing a gradient flow, but in the appropriate metric for F. So we're minimizing some energy. So here's a simple example. Let's take F of rho to be something we've seen before. Rho log rho. Right, this is negative entropy. So we're trying to find a flow that minimizes the negative entropy, in other words, that maximizes the entropy. So we want a flow that tries to maximize entropy. Okay, so what do we need? All we need to do that is we need to come up with the first variation of F. So we know how to do that. Okay, so we need to compute again the derivative of F evaluated at rho plus epsilon chi. Right, this is going to be, write it down, integrate rho plus epsilon chi log of rho plus epsilon chi. Okay, so we take derivative with respect to epsilon. What do I get out here? A derivative with respect to epsilon just gives me a chi times all of this, and I'm going to set epsilon equal to 0. So I'm going to get a term that looks like chi times log rho. And then just product rho, there's nothing complicated here. I keep this fixed and set epsilon to 0, so I have a rho. I take the derivative of this with respect to epsilon. So I get 1 over all of this. So that's a 1 over rho times, so rho times 1 over rho times the derivative of the inner part with respect to epsilon. So that's chi. So I get rho over rho times chi. Okay, so what is my first variation? My first variation, right, is supposed to have the integral of the first variation times chi. So it's just everything that's multiplying chi in here, which is, in this case, log rho plus 1. Okay, so now we want to plug it into our gradient flow, our Wasserstein gradient flow. Some of you are seeing where this is going, I think. Jimmy, what kind of equation is it?
Heat equation?
It's the heat equation, exactly. So, if you don't see it, we'll take this divergence, this gradient rather. All right, the gradient of the first variation. There we go. We'll get there. So the gradient of the first variation is the gradient of log rho plus 1, which is 1 over rho, times the gradient of rho. Okay, we put that into our flow. So the gradient flow is, okay, rho t minus the divergence of rho times the gradient of my first variation. So that's 1 over rho gradient of rho. Just the divergence of the gradient of rho, which is the Laplacian of rho. And I should probably keep my time derivative in here. And so in other words, we have this negative entropy that we want to minimize. Of course, there's lots of ways to do this. If we try to do it via gradients flow in the Wasserstein metric, the flow that we get is nothing but the flow that we get from the heat equation. Okay, so you can think of this as we just came up with a new numerical method for solving a heat equation, the JKO scheme. That's perhaps not so exciting because there's already too many methods out there for solving the heat equation. But this is a simple example. You could put a lot of more complicated F's there and you need a lot of different PDEs. Some of them are very familiar. Some of them perhaps less familiar, some less known about, and this type of scheme gives you a realm for doing some nice analysis. You can learn things that, for example, are preserved by your scheme and by your flows. You could build numerical methods that have important properties. So you may want a numerical method that maintains a maximum principle, for example, which is not always easy to build. Jake works in some of these types of methods, and you know that it's worth trying to build these things, and it's not always obvious how to do. But these JKO schemes will give you a natural way of trying to do something like that, for example. So I'll write down about all the calculations, some other examples. So what are some other examples? Well, we could take our negative entropy and add some other kind of potential onto it, say. And you'll get equations like this, the Fokker-Planck equation. What else? You can have terms like this. This one's kind of interesting. Rho to the m. This gives you a rather more nonlinear equation. Right, and computing these, okay, I didn't make it look easy over here, but computing these PDEs is easy. You just have to get the first variation and then remember what you're taking the gradient of. This is a porous medium equation. And actually this may be less straightforward from a numerical point of view because of the nonlinearity. It becomes harder to build schemes that say preserve maximum principle that you may want in something like this. And the JKL type scheme provide a nice means for this. It's porous medium. You can get some more complicated models. Let's call this grad U of rho. Where U rho is defined to the solution of a Poisson equation. Okay, so given rho, it becomes the right-hand side of a Poisson equation, which you solve to get U and plug into this functional. Okay, and again, it becomes a little more complicated, but you can compute the first variation of these things. You take the gradient, and you'll get now a coupled system here, rho t plus the divergence of rho grad U minus the Gaussian of rho equals 0, coupled to, obviously this equation is important. This is a Keller-Siegel model for chemotaxis, for evolution, say, of a population of cells that are trying to find a move to where there's nutrients. So this would come up in the study of chemotaxis.
The top is just in the focus line?
The top is a Fokker-Planck equation, yeah. Yeah, so it's not a coupled Fokker-Planck equation because in this case, yeah, the V is given to you. And in this case, the potential that we have here is also an unknown. So it's a coupled system.
So what class of functionals does it make sense to look at?
So functionals that are lower semi-continuous and bounded below, and that are functions of these densities, for example. Like, you could try to define these kind of gradient flow type schemes on other metric spaces. You have to redo the analysis depending on what metric space you're on, and in this case, more is known about as tau goes to 0, although I didn't prove that rigorously, that you actually do get convergence to these PDEs. But in general, yeah, you don't need very strong requirements.
So does the convexity of F determine the uniqueness of the solution of the PDE?
Does the convexity of F come in? The convexity of F is not required for these schemes.
No, I'm saying if you had the heat equation and you wanted to prove uniqueness.
So of course, if you don't have something that, let's say, if you want to prove uniqueness of the solutions of the heat equation via this, sure, you could probably do that. But you can do that via convexity of F. It's not, so again, convexity of F isn't needed. What's needed is that you can always define minimizers. Right, so obviously there are other functions beside convex functions that have global minimizers. So what we're asking here is not just for local minimizers, but for global minimizers. So convexity sort of gives that to you, but there are other classes of functions that have that property. But yes, so this will give you a technique for, again, analyzing some of these systems, these gradient flows, or these PDEs, and maybe in one context. Maybe when you're looking at the PD, it's hard to see uniqueness, but then when you go to the JKL scheme, you start to say, oh, it's easy to see that I can build this thing and get unique solutions, or get solutions that preserve certain bounds, for example, which is easier to see in one place than the other place. So existence results, yeah, existence results, maybe not for the heat equation. Obviously, we know a lot about the heat equation. It's a simple example, but for some of these more complicated models, existence results have come out through studying these kind of flows, JKL flows. What else? You can have more complicated models. Some sort of aggregation. Okay, where you have particles, and maybe the potential is determined by what all the other particles are doing. Okay, so W is some sort of potential. And again, you can get some kind of PDE that looks a little messier now. But this would be a model for sort of aggregate behavior. Right, you have motion, you have advection, but the advection is kind of determined by looking at what all the other particles are doing too. And you can do other things. You can combine the different terms that I've showed here into different things. There's models of crowd motion that have this sort of behavior. There's models of computing actually things that look like Wasserstein distances, or sort of one-dimensional slices of Wasserstein distances that you can put in this framework. And it gives, again, techniques for proving existence, uniqueness results, properties of the flow. So we might have, say, in this PDE, looking at this PDE, maybe it's hard to see exactly what's going to happen, but if I know that it's a gradient flow for this functional, I know that this object is always going to decrease, for example. This energy is, I know that this PDE is going to cause this energy to decrease, and I know it because we have these results that this PDE is precisely a gradient flow of this functional. So you can learn properties like this. There's potential. Not much has been done here, and I think it's an interesting problem. The potential for building numerics for some of these more complicated PDEs. Some of them are quite nonlinear or non-local in some cases. And I think it would be interesting to try to use JKL schemes to build numerics here. But nobody's really done that yet beyond really one dimension, I think. But that's one interesting class of sort of flow problems that we get related to optimal transport. I think I posted the JKL paper on Canvas. I'll check and make sure I did. And what else? Santa Brodia's book has a little bit about some of this too, which is kind of useful, I think. Fairly readable. Any other questions?
So, maybe there's any contact functions.
Here? So this would be, I think in this model, it would be an even potential.